Hello everyone, my name is Daniel Rupp and I will present the paper called How Far is Too Far? The Trade-off between Selection Distance and Accuracy during Teleportation in Immersive Virtual Environments. Navigation is one of the most fundamental tasks in every VR application, and a particularly widespread approach is teleportation, where users egocentrically select a target location before being instantly relocated. A common implementation, which is also used in game engines like Unreal or Unity, is to simulate a projectile that shoots out in the forward direction of the controller, following the projectile motion equation. The teleport target location is then determined by the intersection point of this projectile with the scene's geometry. The projectile and the resulting path of the teleport parabola are thereby influenced by the position and angle of the controller, the emission velocity v0 and the gravity g. If we want to change how the teleport parabola behaves, we can only change the initial velocity v0, as we can of course not alter the position and angle of the controller, as this is given by the tracking system, and changing the gravity could make the parabola feel less predictable, as we are so used to Earth's gravity and objects abiding by it. We then formulated the research question: how does the maximal reach of the teleport parabola affect the trade-off between selection distance and accuracy? While the velocity is the parameter that we can adjust, the parameter that we actually alter to select the target point and therefore how far we want to teleport is the controller's pitch gamma. We can already get some insights to answer our research question by just looking at the math behind the projectile motion equation. If we plot the teleport distance on the y-axis and the controller's angle gamma on the x-axis, we get something like this. In our case, a value of -90 degrees means that the controller points straight down, 0 that it is parallel to the ground, and at around 45 degrees we reach the maximal distance that we can teleport to. So what can we learn from this plot? First of all, the plot was constructed for the exemplary velocity of 10 meters per second. If we would have used larger values, the maximal teleport distance would increase and the parabolic curve gets steeper and steeper until we are eventually simulating a straight ray, which we now display in purple for comparison. We can also see that the angle-distance relationship is not linear. For example, when the controller pitches up and down between 0 to 20 degrees, the target location moves by about 4 meters, while between 30 and 50 degrees, the target location moves by less than 1 meter. So if we are tasked to teleport onto a small platform, it is much easier to do so when teleporting close to the maximal value, as the curve's steepness correlates to longitudinal accuracy. But this is of course only true in this two-dimensional setting where we are just thinking about the longitudinal direction and ignore other factors, since especially for larger velocities, teleporting close to the maximal range becomes challenging as the target location is far away and therefore hard to see, and lateral hand jitter increases. We can also see that the straight ray always has worse accuracy than the arc, with the steepness approaching infinity towards 0 degrees. So in order to check whether this holds in practice as well, we want to test this for different velocities and accuracy requirements. When looking into other papers to figure out what values for the velocity or what the maximal reach of the used teleportation technique was, we quickly found out that this is something that is rarely reported in the literature. We looked at 2 review papers, and only 5 out of 27 and 1 out of 13 reported the maximal reach or the velocity of the teleportation technique. If values were reported, the maximal reach ranged between 5 and 180 meters, with around 12 meters on average. Many papers also reported that they used the default implementation provided by the Steam VR plugin, which uses 12 meters. Other commonly used implementations are the XR Interaction Toolkit from Unity, which has a reach of 10 meters, and the VR template from Unreal, which has a reach of 5 meters. So it's not entirely clear what a good parameterization of this value is. In our user study, we therefore sampled 10 different velocities from 6 to 22 meters per second and a straight ray, which corresponds to the maximal reach of 5 to 51 meters or infinity in case of the straight ray, to cover most values used in related work. We also hypothesized that the selection distance is influenced by the required accuracy. So to test different accuracy requirements, participants had to teleport onto 3 differently sized platforms. To answer our research question, we tested upper bounds on selection and asked participants to teleport as far as possible on platforms on a river without missing them. We had 60 participants with a perfect gender balance who completed the study, who in total experienced 10 different conditions with varying velocities, and each participant performed 18 teleports with each velocity. After each teleport, the platform size was randomly changed to one of the 3 platform sizes, while ensuring that each platform size was featured 6 times. This is how it looked like in the application. First, participants had to point to the ground in order to start the selection process, then try to aim as far as possible and teleport onto a platform. To incentivize users to teleport far, we gave them a score that increased with the teleportation distance. If they did not accurately hit a target platform, a loud, unpleasant sound was played and they got a heavy point penalty. So they needed to find a balance between far but also accurate teleports. Now let's look at the results. First, we want to look at the teleportation distance, which is given in meters on the y-axis, and the x-axis denotes the different velocity conditions. The 3 colored lines correspond to the different platform sizes, showing a significant effect of platform size on teleportation distance. We can also see that although people could teleport farther at higher velocities, the teleportation distance plateaued and decreased again, especially for the straight ray. So one explanation might be visibility related, as at some point it is hard to see if a parabola hits the platform or not. That does however not fully explain why the distance decreased again at some point. It becomes clear that something else is going on when we look at the number of failed teleports. In this plot, we can again see that platform size had a significant influence, and the regression analysis also showed that velocity had a significant effect on the amount of failed teleports. If the plateauing of the teleportation distance was just because of visibility issues, the number of failed teleports would plateau as well. However, it steadily increases, so this has to do with the accuracy of the teleport parabola. In the teleportation distance plot, we also showed these red bars, which indicate the theoretical maximal teleportation distance. And from the angle-distance relationship, we learned that if we teleport farther away from the maximal distance, we are on the steeper side of the curve, which leads to increased jitter and therefore decreased accuracy and subsequently more failed selections. However, we can still not clearly say which velocity provides the best trade-off between accuracy and teleportation distance, so we also used a more formalized approach to quantify accuracy by using Fitts law. If you are unfamiliar with Fitts law, it is commonly used for 2D pointing tasks, like a mouse cursor selecting a button on a 2D user interface. The central aspect is a value called index of difficulty, which encapsulates the selection difficulty of a task based on the distance of the selection device to the target and the width of the target. With the time required to make the selection, a throughput value can be calculated. You can then say something like, a mouse has a higher throughput value than a joystick, so controlling a cursor to select a button on a user interface is easier with a mouse than with a joystick. If we want to use this in VR, the question is, how do we determine the distance and width during our 3-dimensional selection? And Copper et al. And Cha et al. Adapted this for 3D pointing tasks by changing distance and width to angular values. So in our case, we had participants point to the floor to start the selection task, and then rotate the controller upwards until they hit the target platform. So in our case, the distance might be something like 120 degrees. The width of the target platform is then the angular difference between the controller angle that just reaches the short side of the platform and the angle that just reaches the far side. So it might be something like 8 degrees. Using these values, we can then apply the ID formula from Fitts law to obtain a value that encapsulates the selection difficulty for each teleport. If we plot this over all of our velocities, we can see exactly what we would expect based on the angular distance relationship. The selection difficulty continues to increase. Note that we only have one line here, since the platform size is already encapsulated in the width parameter that is used to calculate the index of difficulty. Instead of the throughput value, which indicates the efficiency of a selection device, we want an efficiency value for teleportation techniques, which should consider the teleportation distance, as time is less important here. In fact, when looking at the movement time, we can see that the average was around 4 seconds, with not a lot of variation independent of the velocity. So we calculated what we called a teleportation performance metric by changing movement time to teleport distance and flipped around the fraction so a higher value is better. Here we plotted this teleport performance metric, which is given in meters per bits. We can see that the highest value is achieved at 14 meters per second, which indicates that for every index of difficulty we risk during selection, we can teleport 3 meters wide. You can also see that there's kind of a plateau, so anything between 14 and 18 has roughly the same value. We would still consider the lower values better due to the lower index of difficulty associated with it. But of course, ultimately it depends on the requirements of your application. That brings me to the limitations. First of all, our task design had a lower ecological validity, as our virtual environment did not include any elevation changes or rotation, and participants only had to teleport forward. This was, however, necessary to establish a clear causal relationship between the initial projectile velocity and the selection distance, but future work should further evaluate this in more practical use cases. In addition, our user study scenario can be seen as a worst-case scenario, as we assumed that participants wanted to teleport accurately and far at the same time, which is not necessary in every application. If accuracy is not important, for example, higher velocities with less ideal teleport performance can be chosen, which would increase efficiency as larger distances can be traversed more quickly. To conclude, we found that a projectile emission velocity of 14 meters per second, which results in a maximal reach of 21.52 meters, offered the best trade-off between selection distance and accuracy, with an inferior performance of the straight ray. The reason for this can be seen in the angle-distance relationship, and in the future we might want to try different functions like a linear function or even a higher order function to optimize selection accuracy. Thank you very much for your attention. If you have any further questions, feel free to reach out to me or my colleagues.